Guys, welcome to our channel of Sciences and Mathematics. Our discussion for today is going to look at one of the applications of the Nernst equation. And we're also going to see how we can be able to borrow some concepts from maybe the chemical kinetics concept that we discussed, especially on the concentration of reactants and products. So the interaction between the two concepts is going to assist us in trying to find a solution to the challenge that we've posted on the board. And this is going basically to assist us in trying to solve similar questions as we come across them in our discussion. So that is it. Let's just have a look at the question. And then we'll have a discussion of maybe a summary of one or the two concepts that we need in order to find a solution. So the question states that find the cell voltage with a solution of 0.1 molar zinc sulfate solution and 10-4 molar copper sulfate solution. So we have been given in a summary form the standard electrode potential for the two. That is for copper, which is plus 0.34 volts, zinc standard negative 0.76 volts. So as I've said, we're going to look at a slight concept in chemical kinetics, which is going to assist us in trying to interpret part of the Nernst equation that we have already discussed. So from the discussion, of course, we can be able to just write the equation in this case, and then our discussion is going to be centered around that. So we have E cell equals E standard minus 0.0592 1 over n, the log of Q. And my key is going to be copied. So in this case, these different parts of the Nernst equation are very essential for us to understand in order to try and find out how we can be able to have maybe an applicable approach in finding a solution to that one. So in trying to look at this, the E cell in this equation refers to the actual potential of the electrochemical cell setup, and then we have this one, it's a standard potential, and this one N refers to the number of electrons, of course, which are taking part in the spontaneous redox reaction, and the last part, which is Q. This basically refers to the ratio of concentration of the product to the reactants. So this basically is a ratio of the concentration of the product. Oh, sorry for that. That's the concentration of a product to the reactant. So in trying to dissect these different aspects of the Nernst equation, this basically is what it represents for the whole of this setup. And as I said, there is a concept that we are going to borrow from the concept of chemical kinetics, whereby we are going to see that the last Q that I've represented on the board can be given from just a general expression for a reaction, which, if I may just write it. So if we have a general reaction that is, of course, having the reactants as A plus B, which are forming products C plus D, then we can be able to have specific volumes of these reactants and products which are reacting by representing them using coefficients for A, B, C, and D. And therefore, there is a relationship between the concentrations, as we have said, of the specific reacting species and the product species, which can be given as the ratio of the concentration of products reactants that we have referred to as Q in our Nernst equation. So therefore, if we are trying to give Q using this general representation for an equation, we can be able to write it as the concentration of the product D the ratio between the concentration of the products and the concentration of the reactants illustrated as such. So therefore, if you're trying to have a redox reaction which is taking a particular analogy, or maybe we can be able to illustrate using the similar way, therefore we can be able to illustrate this concentration using the same way. So therefore, in the Nernst equation, whenever we are talking about the log of Q, Q is going to represent the concentration of the product, the ratio between the concentration of the product and the reactants. So if I maybe try to still look at part of the equation that we have already written, there are some of the symbols that might be used in that equation which we have to be very conversant with, simply because these equations carries with them some specific meanings that we are supposed to be, or we are supposed to be conversant with. So in this case, there's this specific symbol which has been used in this equation for the superscript for the second E, which we referred to as the standard potential. So in this symbol, this is used to imply the standard potential. Of course, we have talked about the concept of a standard notation, standard units, etc. So this corresponds to the potential. This specifically corresponds to the potential when all reagents involved are in their standard state. So therefore, whenever we are using this particular symbol, it denotes the standard state. And in this case, the standard state is quite different from the standard temperature and pressure that we may be encountering in the discussion about the gas laws. So therefore, for the standard state in this case, it means that we're having 1 molar of solutes, illustrated as 1m, and then with number 2 we have 1 atmosphere. This basically deals with when we were talking about the concept of gases, and therefore this is involving pure substances for liquids and solids. So this basically are some of the conditions that we attach to the concept of standard that we're trying to talk about whenever we're giving this denotation in form of that equation. But we're going to see that if the concentration or the pressure differs from these conditions, the potential will vary from the standard potential, and therefore the actual potential will be not denoted without using that particular superscript. And therefore, as we said, of course, when we were trying to look at the sections of the Nernst equation, we refer that one to as the actual potential, and its value can be, of course, calculated from these other sections of the equation. So therefore, I hope that we have understood the concepts that we have already discussed, and there's one of them, the last one that I'm going to mention, which is of course very much essential, because in case we just insert a figure somewhere, a numerical figure like 1 in that ratio, then it's going to have a meaning, and therefore it's good for us to discuss the reason as to why that one might be done. So in this case, for solids, such as the one that we had written, of course, this is this is a solid. So therefore, I'm trying to illustrate this one. This is a solid aqueous. This is a solid to bridge aqueous. So in this case, the cases whereby we are trying to use that one. So insofar as the concentration is concerned, such as solids like the copper and the zinc that I've illustrated, their concentration is invariant, which means they're going to be given a specific constant, and therefore they are referred to as, or they are said to be at unit activity. they are said to be at unit activity. So therefore, this concept refers to the concept of, whenever we are trying to talk about the concept of unit, it refers to as 1. So therefore, whenever we are allocating 1 to the concentration of those specific species, then it refers to the concept or the fact that they are said to be at unit activity. And therefore the same will be applied to maybe some substances like water and concentrations of other substances that may appear in liquid form in this redox, spontaneous, or maybe electrochemical reactions. So we're going to, I hope that the concept that we have discussed, of course, or the summary is going to assist us in trying to find a solution to the problem on the board. So therefore I'm going to do away with all this so that we can have a space to try and find the solution to that. So fast forward. We're going to find the cell voltage with a solution of a zinc, 0.1 molar zinc sulfate solution and a 10 negative 4 molar copper sulfate solution. So the standard electrode potentials for this one, we can be able to illustrate them using an equation. This is for, of course, copper, which of course we have given as plus 0.34 volts. And then we have given another one for zinc. This is negative 0.76 volts. So therefore we're going to use those specific values in trying to find a solution to our problem. So therefore the solution for this is going to be illustrated as such. We have a general equation for this one. So basically we can be able to represent it using the Nernst equation, but I'm going to use also an alternative procedure and maybe basically also use the Nernst equation in that specific order to find a solution. So we can write this one as E oxidation minus E reduction. Now that we have talked which parts of the cell are going to be represented by that. So I can still expand this equation in order to represent which species are undergoing oxidation. So therefore still E cell can be represented as E. So the species that is undergoing oxidation is copper. So we have copper. And then the species that is undergoing reduction is so maybe this is not necessary. I'm just going to, so the species that is undergoing reduction is going to be zinc, and therefore in this case we are going to just have the demonstration for copper minus positive. So for copper this is going to be given as using the Nernst equation. It's going to be given as E standard for copper and then 0.591 over 2. So we're going to see that in different usage of this particular numerator for this second part of the Nernst equation, it's either going to be 1 or 2, and maybe there's going to be that slight variation according to different texts that we're just using. So in this case we might find us using either 1 or 2 for the last figure, but that's just simply the same for that. So we're going to have a concentration for copper and a concentration for copper ions at the denominator for Q. So this is from the standard potential for copper. We have been given as plus 34 plus 0.34 minus 0.0591 over 2. 2 specifically implies the number of electrons that are being used in this, of course, the reduction process. And we're going to see that this is going to be given for log. So therefore, the last statement that I mentioned about the solids and other pure substances, I'm going to give it as a unity activity, which is 1. over the concentration of the copper solution, which is given as 10 negative 4. So therefore, basically this is going to give us the E cell for copper, and this is going to be plus 22 volts. So this is where we're going to just have to reserve it somewhere because of space. So this is plus 22 volts. That is for copper. So secondly, we're going to use the same procedure to try and find out the E cell for zinc using the Nernst equation. Of course, we're going to have the E cell for zinc being represented as, just write this one, E zinc E zinc standard, zinc positive, and we put this outer part of the Nernst equation, the log of the concentration of zinc over the concentration of the ions of zinc. And that basically, if we do a substitution, is going to give us, we can just do maybe just a confirmation from our calculations to ensure that the figure is correct, 79 volts. So therefore, having found the E zinc, E actual for zinc and E actual for copper, so for zinc it's going to be basically 0.79 negative volts. So therefore, for us to find E cell as per our first expression there, it's going to be, that is E cell for copper, which is, E cell for, just so we do a substitution for that, and we will get that this is a positive 0.22, and then minus 0.79, which is going to be plus 1.01 volts. So kindly do just a calculation to confirm the same. So in this case, using the Nernst equation and the two parts of the electrochemical cell for half equations for those specific reactions, we can be able to find the E cell for the electrochemical cell that is made up of copper sulfate and zinc sulfate solutions using those specific approaches. So essence for us is was to try and understand why these specific notations are being used. Number two, in trying to find the general expression for trying to find another alternative for representation of E cell apart from the Nernst equation that we have already been discussing about. And those basically two concepts are going to assist us in finding a solution to questions such as the one that we have illustrated on the board. Now, with that one said and done, I hope that we have understood how we can be able to represent these different forms of E cell equations using the Nernst equation and the general expression that of course we have listed on the board, which is of course E cell is equals E oxidation and E reduction. So that is it for today. Bye guys, God bless.